All right, today's lecture is on normal approximation. Normal approximation to the binomial distribution. So I'm going to shorthand that binomials, okay? So one thing that is crucial for you to know is you're doing a binomial distribution problem, but you're going to use the normal distribution to solve this binomial distribution problem, okay? For example, let's say I want to flip a coin 100 times. Find the probability of 55 or more heads. Okay, I guess that's not a question. Just find the probability of 55 or more heads. All right, so this is a binomial distribution problem. Does everybody agree with that? What is n in this problem?
100.
100, great. What is p? What is the probability on one flip of a coin that you get a heads? It's 0.5. Okay, and what x's am I looking for? If I want 55 or more, what x's are we talking about?
55 to 100?
55, 56, all the way up to 100, right? So 55 to 100, or x is greater than or equal to 55. Okay? Now the question that I posed to you is, how would you solve this problem? Well, one thing is you could go to your table in your book, right? And you could go to n equals 100. But that's going to be a short trip. Why? Because what's the highest n we have in our book? 20 or 25, right? It doesn't go all the way to 100, okay? But let's just say for the sake of this question, let's say there did exist a table that went up to 100, okay? How would you look this up in the table? Well, you'd go to x equals 55, write that number down, then 56, write that number down, then 57, and you have to write all those numbers down and then add those up, right? So that's going to be a pain that we don't want to have to deal with, all right? So really, right now, the only way we have to solve this problem is using technology, okay? But I'm pretty sure the technology that we utilize does the normal distribution to solve it, okay? So we can't do this problem by hand as is. What we're going to have to do is use normal approximation, and that's what today's lecture is. So we'll come back and solve this problem in just a minute, but let's see how to do it. Okay, so if you're going to use a normal distribution to approximate, there's a couple of conditions. The first thing is n times p and n times q both have to be greater than or equal to 5, okay? So we have to check that real fast, that n times p and n times q are greater than or equal to 5. And the last example we just did, we had n was 100 and p was 0.5. So 100 times 0.5 is 50. So that's clearly much larger than 5. So we'd be okay to do the last problem. Okay? All right, so in binomial distribution land, we have n, p, q, x, right? And in normal distribution land, we just have two things. What are those two things? Mean, standard deviation, okay? And then what area you're trying to shade in. Okay, so this is what we have going on over here. And we're trying to shade in some area, right? So we're going from what we call a discrete distribution, where we have np, x equals 5, or x equals 6, or x equals 7, to a continuous distribution, where we're looking at an area, right? What's the probability that it's to the right of this value? We look at that area and solve it, okay? So there's a couple of things. One of the great things we talked about with the binomial distribution is there's a good, easy formula to find the mean. What was the mean of a binomial distribution problem? The expected value. Does anybody remember the formula for that? It was just n times p. Okay, and that's going to be really important because when I use a normal distribution, I need to know what that mean is. So it's n times p. Great. That's going to help me a lot. the variance over here was NPQ. The standard deviation then was the square root of NPQ. Okay, so that's what we're going to use over here, square root of NPQ. So that was pretty easy. Those are just two formulas. Okay. Then there's one more thing that we have to take into account, and that's something you definitely want to put in your notes, and that's called continuity correction. And we have to apply this continuity correction when we're going from a discrete distribution to a continuous distribution. Okay? So I'm going to talk for a few minutes on this continuity correction factor, and hopefully you can kind of see it with your eyes, and then it'll be more clear when we have to do it. Okay? So let's take a look at a picture, and hopefully we can see this with our eyes. So, how do I apply continuity correction? Okay, what I want to do here is let's just make kind of sort of a histogram. Okay, so let's do a histogram for a binomial distribution. Let's say n is 6 and p is 0.5. Okay, so x could be 0, x could be 1, 2, 3, 4, 5, and 6. The only reason why I'm doing this graph is just to hopefully help you guys see what happens with this continuity correction. Okay, so I need a little bit of help. What I want you to do is go to your table in your book, go to n equals 6 in the binomial distribution table, p equals 0.5, and then I want you to look up these x values. Okay, so open up the binomial distribution table, go to n equals 6, p equals 0.5, and then look up these values for me. And I'm going to kind of make a little bit of a histogram with it. Okay? So when you look up x equals 0, what does it give you? .016. Does everybody see that? So we're at n equals 6, p equals 0.5, x equals 0. Should be 0.016. Does everybody see that? So I'm going to kind of make a little histogram here, 0.016. Okay, good. Let's go up to 1. What is 1? 0.094. Great. So that's a bit higher. 0.094. Let's move over to x equals 2. What do you get for 2? 234, so we're getting higher. 0.234. And let's go to 3. 312, a little bit higher again. Is everybody with me on these values?
No.
Binomial distribution, n equals 6, p equals 0.5. It's in the back of your book, the binomial distribution table. So the table that you use to look up binomial probabilities. And then we're at n equals 6, p equals 0.5, and then we're just looking at the individual x values. Okay? So at 0 we got 0.016, and at 1 we got 0.094. Okay? And I'm continuing on now. When we get to 4, it goes back to 234, right? So 234. And then 5 goes back to 094. Does everybody see that? And then 6 goes back to 016. Okay? Now, the reason why I'm drawing this picture is because I want you guys to visualize and hopefully visually see that, hey man, this kind of looks like it could be normal-ish, right? Does everybody see that? To see how this picture kind of looks normal? Okay. But now, here's where the problem exists. Over here in binomial land, I would just say, what's the probability x equals 3? Right? And you would just look it up in the table and say 0.312. Okay? That doesn't work in the normal distribution, right? In the normal distribution, what do? I have to have a starting point, an ending point, and the area between, right? Or a starting point here and an area to the right, or a point here and an area to the left. That's pretty much the three cases. Is everybody with me on that? So you need some lines and then the area between those lines, okay? So that's what we're doing right now. It's called CC, continuity correction. Okay, so using this picture here, let's say you want the probability in binomial land that x is bigger than 2. Actually, let's start with just x equals 2. Sorry, let's start there. The probability that x is equal to 2. Okay? That's where we're going to start. So I would just look up this value. But when I go to the normal distribution, I want to actually shade between this number and then find that area. Okay? So just kind of looking at this graph here, what number would you say that I'm starting at, and what number would you say I'm ending at, and shading in between? 1, 3. What is this value right here?
1,
It's right in between 1 and 2, so 1.5. And what is this value here?
2.5.
2.5. Okay? So that's what we're going to do. When we go to normal, we're going to go in between and shade from 1.5 to 2.5. Okay? That's called continuity correction. Okay? So in binomial, it's probability that x is equal to 2. When we shift it over to normal, it's going to be the probability that x is between 1.5 and 2.5. That's what we mean by a continuity correction. Okay? All right, let's do another one. Over here, let's say the question was, what's the probability x is bigger than 4? Okay, now be careful. In my binomial distribution, if I say x is bigger than 4, what am I actually starting with then? 5, right? So I want 5, and I want 6. Does everybody agree with that? So I'm starting at 5, and I'm going to 6. So shading-wise, when I go to the normal, I really want to start right here. And what point is that? 4.5. Great. So when I shift over here, it's going to be x is bigger than 4.5. Okay? Does everybody see that?
No.
So bigger than 4, I'm starting at 5. When I shift that over to the normal distribution, I'm shading, I want to take in a little bit more area, so you're starting at 4.5. Okay. Let's try the probability that x is less than or equal to 3. Less than or equal to 3. So in normal distribution land, if I'm doing x less than or equal to 3, I'm including 3 and 2 and 1 and 0. So where am I going to start over there? I want to start right here. So it's a little bit to the right of 3, which is 3.5. So over here, kind of ran out of room here, but you want the probability, just put it over here, the probability that x is less than 3.5. Okay? So the general thing that's happening is figure out the area that you want, and then you're going to have to go a little bit, and when I say a little bit, you're going to have to go 0.5 in the direction to get more area. Okay? That's how it works. And that's continuity correction. Okay? So to do the normal approximation to the binomial distribution, you're going to make it a normal distribution problem using the mean, using the standard deviation. So the one thing that's key to getting it correct is you have to apply the correct continuity correction factor. Okay? Let's do some examples and hopefully it'll be more clear. Okay, so let's go back to the first example we put on the board today. Back to example 1. We're flipping a coin 100 times, right? And I wanted the probability of 55 or more hits. Okay? So we're going to use the normal distribution to solve this problem. Okay, so if I use a normal distribution, and I'm using normal approximation, I have to write down 3 things right away. First thing I need to know is, hey, what's the mean? Then I need to know what's the standard deviation? And then I need to apply the correct continuity correction. Okay? Okay, great. So in this problem, what is the mean? What is n times p in this problem? N is 100, p is 0.5, so we get 50. Great, so my mean is 50. All right? The standard deviation is the square root of n times p times q. Okay, so take that to your calculator. And we'll round it off, so 100 times 0.5 times 0.5. Oh, comes out really nice, just 5. Okay, now let's be careful here. So, you know, somewhere I have 55, 56, 57, dot, dot, dot. Here's 55, here's 56, here's 57. Okay, and we want 55 or more. So I'm including 55 and everything to the right. Okay, so starting at 55, I'm going everything to the right. So starting at 55, I need to go a little bit to the left to get that starting point. Okay, so the continuity correction factor here is I don't start at 55, but in fact I go a little bit to the left and start at 54.5. Okay, so continuity correction, I want to do x is bigger than 54.5. Okay? Now this problem is just a normal distribution problem. Here's your mean, here's your standard deviation, here's the picture we want. Just solve it. Okay? So draw your picture. The mean is 50. X is 54.5. And I want area to the right.
Oh, because x is bigger.
Yep. Right, it's 55 or more. So to the right. Okay, how do I solve this? How do I do a regular normal distribution problem? I transform it to a z distribution. So I have to convert it to a z value. So we have 0, and I need to know what that z value is. What's my formula for that?
X minus x squared.
Right. So 54.5 minus 50 divided by, what was my standard deviation here?
5.
5. Great. So plug that into your calculator. And you get 0.90, it looks like. So these numbers are working out really nice. So now here's my picture. Now the question just becomes the very beginning of this chapter, right? Find the area to the right of z equals 0.90. So I open up the normal distribution book now. And if I look at 0.90, it gives me area to the left. What area does it give me?
0.8159.
For looking at 0.90, what area is this?
0.8159.
8159? Okay, great. So my area is going to be 1 minus 0.8159. And I will let you tell me what that is. 1841. Okay. 1841. And that's it. So what we did is we tackled a binomial distribution problem, but we did it with the normal distribution. Okay? So you need to know the mean, you need to know the standard deviation, and you need to apply the correct continuity correction. Okay, so this is a big one, 3, doing the correct continuity correction. Question?
So why did you subtract 0.5 in this one to get your CC, and the other ones you added 0.5?
Okay, great question. So you don't want to memorize that I added 0.5 or subtracted 0.5. You just want to go in the direction that will give you more area. Okay? So in this problem, I was trying to illustrate here. We have 54, 55, 56, 57. I want 55 or more, so I'm including 55 and I'm going to the right. So I need to go a little bit to the left to include more area, okay? Let's just do a couple more examples of just doing continuity correction, okay? So let's make sure we're clear on those. Okay, let's do, this is your binomial. And then let's do the correct continuity correction for normal. Okay? So let's start with probability x is bigger than 5. So in normal distribution land, if you're bigger than 5, where do you actually start?
4.5.
Where do you actually start in just before continuity correction? Where do I actually start if I'm starting at bigger? You actually start at 6, right? Is everybody with me? If x is bigger than 5, you're starting at 6, okay? So I want to start at 6, and I'm going to the right, but I need to go a little to the left to include more area. So what's a little bit to the left of 6? 5.5. Okay, does everybody see that? So it's really important to know where we're starting here. If it's bigger than 5, you start at 6. What if it was greater than or equal to 5? If it's greater than or equal to 5, where do I actually start? 5. So I'm starting at 5 and I'm going to the right. So I need to go a little bit to the left, which would mean I'd start where? A little bit to the left of 5
4.5.
4.5. Okay, do you kind of see that a little bit? Let's do less than problems. Let's say it's less than 10, okay? In binomial distribution problems, if you're less than 10, where do you go to? Up to what? Up to 9, right? It's up to including 9 if you're less than 10, okay? So I want to go up to 9, and I'm going to the left, so I need to go a little bit to the right, just to include just a little bit more area. So we're going to go to 9.5. Okay. Question number 4. What if it was the probability that x is less than or equal to 10? If you're less than or equal to 10, you're including 10, right? So if I'm including 10 and I'm shading to the left, I need to go a little bit more than 10 to the right. So where would I go to? 10.5. Okay? If it's equal to, it's kind of actually easier. The probability that x equals 6. So if it's equal to 6, I just want to shade in 6, right? But I can't just shade in 6 in the continuous, so I go a little bit to the left and a little bit to the right. So what do? 5.5
X.
to 6.5. I have on the board every possibility, okay? This is pretty much every possibility you can have. So don't memorize, oh, I always add 0.5, or oh, I always subtract 0.5. It's not like that. You need to know where you're shading, and then just go a little bit more to the left or right to include more area. Okay? All right, let's try another binomial problem where we use normal approximation. All right, let's see. A baseball player has a hitting average of 0.285. Okay? What is the probability of getting at least 300 hits in his next 1,000 bats. Okay? Baseball player has a hitting average of .285. What's the probability of getting at least 300 hits in his next 1,000 trips to the plate? All right. I want to use normal approximation to solve this problem. Okay, so if I want to do a normal distribution problem, there's three things that I need. I need the mean, I need the standard deviation, and last but certainly not least, I need to do the continuity correction. Okay. What is the mean for the problem? Let's start there. So I need n.
1,000 times.
What is n?
1,000.
N is 1,000. Great. What is p in this problem?
0.5. No?
So if p would be 0.5, if this hitter had a 50% chance of getting a hit.
It's 0.28.
Yeah, it's 285, right? We actually stated that his probability of getting a hit with one bat at the plate is 0.285. So 0.285. Great. So if you do that in your calculator, what does that come out to? Yeah, you don't really need to do that in your calculator, but yes, 285. Great. The standard deviation for this problem is what? Square root n times p times q. If p is 0.285, what is q? 0.715, right? Great. So do that in the calculator. And let's go ahead and round that off if we need to. So 1,000 times 0.285 times 0.715. Okay, let's go 4 decimal places. So 14.2750. 14.2750. Okay, continuity correction. At least 300 hits. Okay? At least 300 hits. So I'm including 300 and everything to the right. Okay? So think it in terms of shading. I'm starting at 300 and I'm going everything to the right. So I need to go just a little bit to the left. So where would I start? 299.5. Great. So x is bigger than 299.5. Okay. If I can make it through those 10 minutes right there, then this problem is just a regular normal distribution problem. Okay? Here's your mean, here's your standard deviation, here's what you're trying to find. Put a picture on the board, then convert it to a z, then solve that area using your chart. Okay? That's all I have left to do now. So go ahead, take a few minutes. I'll work on it as you're working on it. Draw some pictures for me, and then convert it to a z. See if you get a z value of approximately 1.02 when you round it to 2 decimal places. .02. So double check, take your time, and see if you get 1.02.
I got 1.05.
1.015?
1.05.
1.05.
1.05.
Huh. Alright, what did I mess up?
I guess you
290?
got.
Yeah, 1.02.
You didn't mess up.
Okay, so maybe I didn't mess up. Did you guys do 299.5 minus 285 divided by 14.2750?
I did 300.
Oh, okay. Yes, you forgot to do the continuity correction. Make sure to do 299.5. Alright? Small things will make a difference. So, try to get z equals 1.02. If you look up 1.02, it's going to give you area to the left. So our answer will be 1 minus that, or the opposite of that. Okay? So look up 1.02, and you get 0.8461. And finally, our answer is going to be 1 minus 8461. .1539. Okay? So again, we solved this problem. It was technically a binomial distribution problem, but we solved it using the normal distribution. Question?
So you don't need to find the probability of getting all 1,000 hits and find it in between. It's just you just find it one way.
Right. Yeah. Exactly. So you're by doing this, you're finding the specific area that you want. Yeah. Okay.
It's at least 300.
Okay. So one last thing that we want to talk about. Okay, so we have 3 types of problems that all look somewhat similar, okay? So you have regular normal. How do I know it's a regular normal problem? It's somewhere in the problem that says it's normal, right? Also, it's usually speaking of an individual, right? An individual is selected. What is the probability that individual is greater than 5 or blah, 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 whatever it is, okay? CLT, it's not an individual, right? It's a group of some size, n, right? So a group of 40, what's the probability? The mean of that group, the mean of that sample is blah, 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 okay? So you're always seeing something like the mean of the group, or the mean of the sample, okay? And that's a CLT problem. Then today what we did was normal approximation. So a normal approximation problem, you can tell, because it's a binomial distribution problem, but the numbers are generally pretty large, so they're off of our chart in our book, okay? And so you're going to use the normal distribution to do this binomial problem. So it's going to give you stuff like n and p and x. But what you're going to do is use the normal to solve it. Okay? And don't forget CC, continuity correction. When these questions are all mixed together, they look very similar. So you have to be very detailed in looking for clues on as to what problem it is. So regular normal, you have a mean, you have a standard deviation, you have an individual selected, what's the probability the individual is, blah, blah, blah. Okay? CLT, it's the mean of the group or the mean of the sample. Normal approximation, it's a binomial distribution problem, and you're going to use the normal distribution to solve it. Questions? All right.